Alright, welcome back to the AI Research Roundup. I am your host, Alex. Today we're looking at a fascinating paper called OmniAudio, Generating Spatial Audio from 360-degree Video. So we all know that for things like virtual reality to feel real, the sound has to match what you're seeing. The problem is, most video-to-audio models generate flat, non-spatial audio. This paper tackles that by generating spatial audio directly from 360-degree video. Specifically, they produce something called first-order ambisonics, or FOA audio. This is a special audio format that captures sound directionality, creating a full 3D soundscape. To achieve this, they propose a new framework called OmniAudio. And for any developers listening, the authors have also released the code for this work on GitHub. It's a full PyTorch implementation that includes everything you might need to try it out. This includes inference code, pre-trained models, and even the large-scale Sphere 360 dataset they curated specifically for this research, which is always fantastic to see. So let's take a closer look at the model architecture. So this first figure really illustrates the core problem the researchers are trying to solve. On the left, you see a comparison between a normal video and a 360-degree panoramic view. With the normal view, a train just pops in and out of frame. But the panoramic view captures the entire scene. You see the train coming and going. Then, on the right, the figure shows the audio difference. With standard stereo audio, if you turn your head, the sound doesn't change. It's stuck. But with first-order ambisonics audio, the sound correctly shifts, maintaining its position in 3D space. Alright, so a huge challenge for a task like this is simply having the right data. This table really shows the gap the researchers were trying to fill. It compares their new Sphere 360 dataset to existing ones. You can see that most datasets are missing a key ingredient. They either don't have 360-degree video, or they don't have the crucial first-order ambisonics audio. Sphere 360 is one of the few that has both, and at a massive scale. Over 100,000 clips totaling 288 hours, all specifically for audio generation. Okay, so this diagram shows us how the OmniAudio model actually works. It's a two-stage process. First, on the left, is the self-supervised pre-training. Here, the model learns general audio features from a huge amount of both non-spatial and spatial audio. It uses a component called a variational autoencoder, or VAE, which is a network that learns to compress and reconstruct audio, and then feeds this into what's called a diffusion transformer. Then, the second stage on the right is the video-guided fine-tuning. This is where the model uses two video streams, both a standard perspective view and the full 360-degree video, to guide that diffusion transformer in generating audio that is perfectly synced with the panoramic visuals. Alright, so after all that complex pre-training and fine-tuning, the big question is, how well does it actually work? Well, this table lays out the results, and they're pretty clear. It compares OmniAudio against other models, both on the Sphere 360 dataset it was trained on, and on a different one it has never seen before. The table uses several metrics, like Frechet distance and KL divergence, which measure audio quality, and delta angular, which measures the error in the sound's direction. For all of those, a lower number is better, and OmniAudio, shown in bold, wins across the board. So a key part of the OmniAudio design was that dual branch approach, using both the full panoramic video and a more focused perspective view. This table digs into whether that was really necessary. It's what's known as an ablation study, where you test the model with different parts removed. The rows show the model's performance using just the panoramic view, just the perspective view, or both together. And the results in the top row, which is the full model, are consistently the best. This shows that combining both the global context and local detail is what really makes the difference. And beyond just the numbers, this figure gives us a great qualitative look at the results. These are visual representations of the sound, called spectrograms, for two different video scenes. Each row shows the output from a different model, with the real-world audio, or ground truth, at the very top. You can see the 4 channels of the first-order ambisonics audio we talked about. On the left, a machine moves behind the viewer. You can see in the ground truth and the audio space output how the directional channels, especially X, capture this movement. The other models really struggle to create that dynamic spatial effect. Okay, and remember that two-stage architecture we saw earlier? This table shows just how important that first self-supervised pre-training stage is. It compares 4 different setups: the full course to fine strategy, just the fine-tuning part, just the course part, and no pre-training at all. Looking again at our metrics for audio quality and spatial accuracy, where lower scores are better, the top row representing the full model wins out. This result really drives home that teaching the model general audio characteristics first is a critical step for achieving the best spatial audio generation later on. When we put all these pieces together, it's clear the OmniAudio approach is really effective. The combination of that dual-branch architecture and the 2-stage pre-training process allows it to generate spatial audio that's not just high quality, but also accurately placed in 3D space. This is a huge step forward for creating truly immersive, virtual, and augmented reality experiences. That's all for this episode of the AI Research Roundup. Thanks for listening. I'm Alex.